A black hole can be so large that if you placed it where our sun is, the point of no return would not end near Mercury, or Jupiter, or even Neptune. It would keep going, past the familiar architecture of the planets, past the neat little map most of us still carry in our heads when we hear the words solar system, past Pluto. Far enough that the comparison itself begins to fail, because the scale is no longer something the mind can hold as an object. It becomes an environment. That is TON 618. And strangely, that is not the most unsettling thing about it. The first shock is size. The deeper shock is that size is only the symptom. Because the universe is full of large things. Galaxies are large, nebulae are large, even the black hole at the center of our own galaxy, Sagittarius, a star, contains around 4 million times the mass of the Sun. By any ordinary standard, that is already absurd. It bends the orbits of stars. It anchors the dynamics of an entire galactic core. If you were trying to invent an object big enough to humble the human imagination, 4 million suns compressed into one gravitational well would seem sufficient. TON 618 is not sufficient with that comparison. It is not merely bigger. It is larger by the kind of margin that makes one extreme object start to look local, almost provincial. The black hole associated with TON 618 is estimated at around 66 billion solar masses, not million billion. Its event horizon, that boundary beyond which no signal can return, would stretch out to a scale dozens of times farther than Pluto's orbit if it were dropped into the center of our system. The circumference of that horizon would be measured not in a few elegant equations on a page, but in weeks of light travel time. Even light, moving at the fastest speed the universe permits, would need more than a month just to circle the edge. That is when the word object starts to feel dishonest. An asteroid is an object. A planet is an object. Even a star still feels, in some deep intuitive way, like an object. This does not. This feels like a region of reality where scale itself has become hostile to common sense. And yet we do not know TON 618 because astronomers somehow photographed a black sphere hanging in space. We know it because from more than 10 billion light years away, something in that region blazed so violently that it could not be ignored. The light reaching us from TON 618 has been traveling for roughly 10 billion years. When that light began its journey, Earth did not exist. The sun had not formed. Our planet, our oceans, every mountain, every city, every memory any human being has ever had, all of it still belonged to the future. What we are seeing is not a distant place. It is an old event. We are looking across such an enormous depth of time that distance becomes a kind of archaeology. And there, in that early darkness, sits one of the most luminous quasars ever found. That detail matters, because TON 618 is not famous for being a quiet black hole. Quiet black holes are almost impossible to see. A black hole becomes visible only when its surroundings betray it, when matter falls inward, compresses, heats, and radiates with catastrophic efficiency before it disappears. TON 618 is visible because the region around it is burning with a brilliance that outshines entire galaxies. Not a cluster of stars, not a bright nebula, whole galaxies. That means the black hole is not just large, it is feeding. And it is feeding at a scale the human mind almost refuses to picture honestly. Try it anyway. Imagine gas clouds larger than stellar systems, falling inward over immense spans of space. Imagine gravity taking material that might once have become stars, planets, dust, or cold darkness, and instead driving it into a tightening spiral. The farther inward it falls, the faster it moves. The faster it moves, the more violently it collides with other infalling matter. Motion becomes heat. Heat becomes radiation. The darkness at the center remains dark, but everything around it begins to glow with the kind of intensity that makes stars look chemically modest by comparison. A black hole shines brightest just outside itself. That is one of the great insults physics delivers to intuition. We call it a black hole, and the name suggests absence, emptiness, a kind of cosmic hole punched through existence. But the most visible black holes in the universe are not known to us by darkness. They are known by what matter suffers before the darkness takes it. TON 618 is one of the clearest examples. Its luminosity is estimated at roughly 140 trillion suns. That number is so far past useful human scale that it risks becoming decorative, just another giant figure in a genre already crowded with giant figures. But the reality beneath it is more severe. It means this quasar is releasing energy at a rate that no ordinary stellar process could sustain. Nuclear fusion, the mechanism that powers stars, is efficient enough to light the cosmos for billions of years. Black hole accretion is harsher, more efficient, more violent. Matter falling toward a black hole can convert a remarkable fraction of its mass into radiation before crossing the horizon. So, TON 618 is not just sitting there as a monument to gravity. It is an engine. A gravitational engine so vast that if it were somehow moved anywhere near our cosmic neighborhood, it would not merely dominate the sky. It would rewrite the meaning of sky. From the distance of Alpha Centauri, the nearest star system to our own, an object this luminous would blaze tens of thousands of times brighter than our sun appears from Earth. From the distance of the Milky Way's center, it could still rival the brightest natural objects we see, bright enough to cast shadows. This is not ordinary brightness magnified. This is matter being forced through one of the most efficient energy release processes the universe allows. And still, that is not the deepest problem. Because if TON 618 were simply an ultra-massive black hole in the mature universe, it would already be extraordinary. It would already deserve awe. It would still be a natural monument to how far gravity can go when given enough matter and enough time. But time is exactly where the comfort disappears. The light from TON 618 comes to us from a universe that was far younger than the one we inhabit now. We are not seeing this object at the end of cosmic history, after endless billions of years of patient growth. We are seeing it when the universe itself was still in a more violent, unfinished phase. Galaxies were still assembling. Star formation was more intense. Matter was more abundant, yes. But cosmic history was also shorter. The clock had not been running nearly as long. And that changes the feeling of everything. Because large things are easy to explain with deep time. Deep time is one of the mind's favorite anesthetics. Give any process enough billions of years, and impossibility softens into patience. Mountains rise, continents drift. Stars are born and die. Galaxies merge. Even the strange starts to feel permissible, once time is allowed to do the quiet work of making extremes seem earned. TON 618 does not fully allow that comfort. It is too large, too luminous, too developed too early for the reaction to remain simple awe. Awe is where the story begins, but very quickly awe matures into something sharper. A question. Not how can something be this big? How did the universe build it this soon? That is where TON 618 stops being a record holder and becomes a problem. Because size alone is spectacle. Size plus timing is a fracture in intuition. And once that fracture opens, the black hole changes in front of us. It is no longer just a giant dark sphere ringed by incandescent matter. It becomes evidence. Evidence that the young universe may have been able to grow structure faster, harder, and with less regard for our sense of plausibility than we instinctively expect. The solar system comparison is only the bait. The real story begins the moment that comparison stops being enough. Because the deeper we look at TON 618, the less it resembles an oversized black hole, and the more it resembles a challenge to our quiet assumption that the universe builds its greatest structures slowly, reasonably, and in emotional proportion to the minds trying to understand them. It does not. And to see why, we have to leave behind the shock of its size and enter the far more dangerous question hidden inside it. Not what TON 618 is, but how a universe still so young managed to make one at all. Because that question changes the emotional geometry of the whole thing. A gigantic black hole at the end of cosmic history would still feel extreme, but not destabilizing. Give the universe enough time, and almost any enormity starts to sound negotiable. Time has a way of laundering shock. It turns violence into process. It makes the improbable feel patient. A mountain range can rise grain by grain. A galaxy can be assembled from mergers so slow that no single generation of stars would ever notice the plan. Even a black hole of impossible size can be made to feel almost reasonable if you imagine it growing in the dark for long enough. But TON 618 is not coming to us from the old universe. It is coming to us from a universe that was still young enough to feel unfinished. The light we receive left that quasar when the cosmos was only a few billion years old, roughly a quarter of its current age. That matters more than the raw distance, because distance in astronomy is never just spatial. It is historical. The farther we look, the earlier the universe becomes. So, when we look at TON 618, we are not simply seeing something remote. We are seeing a black hole already operating at an absurd scale, while cosmic history was still in one of its violent early chapters. That should make us uncomfortable. Not because the universe was chaotic. We expect that. The early cosmos was denser, richer in gas, more collision-prone, more fertile in certain ways than the quieter universe around us now. Galaxies were feeding, merging, assembling themselves through repeated acts of gravitational theft. Star formation was more intense, quasars were more common. There was abundance, motion, instability. In that sense, the young universe was a good place for growth. But good place for growth is not the same thing as good place for this. That distinction is everything. It is one thing to say the early universe could build fast. It is another to say it could build this fast. Because TON 618 is not just a large black hole caught in a convenient moment of feeding, it appears as an already mature gravitational system, already operating like a cosmic power plant, already luminous enough to rival entire galaxies, already massive enough to make our own central black hole look less like a sibling and more like an apprentice. By the time the light we now see began its journey, TON 618 was not becoming outrageous. It was already outrageous. And that means the real mystery is not located in the image we imagine when we hear the words black hole. It is located in the history we do not see. Somewhere before that ancient light left for Earth, matter had to fall inward for ages. Gas had to find its way to the center instead of becoming only stars. Angular momentum had to be bled away. Whole galactic environments had to cooperate, or at least fail to resist. Growth had to happen not once, but repeatedly, and at rates that do not sit comfortably inside the human instinct for how long extreme things should take to become extreme. That instinct is more fragile than it seems. We carry around a hidden belief that scale and time should roughly match. Small things can form quickly. Vast things should take longer. The more enormous the structure, the more history we assume must be stacked beneath it. It is not a scientific law. It is a psychological one, a way of making the universe feel morally arranged, proportionate, comprehensible. TON 618 violates that feeling. It does not merely seem large. It seems premature, and premature enormity is a different kind of disturbance. It implies that the universe can cross thresholds before our intuition is emotionally prepared to authorize them. It implies that growth, under the right conditions, is not a steady climb, but something far less comforting. Something that can lurch, accelerate, condense, and arrive already oversized. That is why the size comparison to the solar system, however useful, is still only the outer shell of the story. It shocks the imagination. Yes, it tells you that the object has escaped ordinary scale, but it does not yet tell you why astrophysicists care about monsters like this. Scientists do not lose sleep simply because nature has produced something dramatic. They lose sleep when an object threatens to compress too much history into too little time. TON 618 comes close to doing exactly that. You can feel the problem if you strip away the rhetoric and keep only the clock. Black holes do not emerge from nothing. However strange they become, they inherit their future from earlier structures. Somewhere in the first generations of cosmic growth, there had to be a beginning, some initial seed, some early collapse, some first act of the concentrated gravity. From there, the black hole could feed, it could merge, it could gain mass through long intervals of accretion. But all of that still has to obey one brutal constraint. The universe had not been alive for very long. So every extra billion solar masses begins to feel like a historical accusation. Not against the data, necessarily, against our comfort. Because if TON 618 was already this large in that era, then the young universe was not merely busy. It was efficient in a way that strains the imagination. It was capable of delivering matter inward, sustaining luminosity, and building hierarchy at rates that do not feel gradual. The familiar story, stars form, galaxies mature, black holes grow at stately cosmic speed, begins to sound too calm, too domesticated, too much like a version of reality adjusted for human nerves. The actual universe was under no such obligation. This is where the phrase young universe can mislead us. It sounds almost gentle, as if the cosmos were in a kind of infancy. But infancy, in astronomy, does not mean small or simple. It often means denser, hotter, more collision-rich, less settled, more willing to produce extremes. A young forest is chaotic. A young ocean world is violent. A young universe is not an innocent universe. It is a universe with fewer breaks. That matters because once you stop imagining early cosmic history as a patient prelude and start seeing it as a period of intense gravitational opportunity, TON 618 becomes less like an impossible miracle and more like a clue. Not a violation of physics, but a revelation about which parts of cosmic history were more aggressive than our intuition prefers. Still, a clue is not an explanation. We know the universe was capable of making luminous quasars early on. We know supermassive black holes were already present when the cosmos was much younger than it is today. The evidence for that has accumulated for decades. But TON 618 lives near the outer edge of that pattern. It sits where the question sharpens. Not can the universe build big black holes early? We already know the answer to that is yes. The more precise and dangerous question is this. How early can growth become excessive before our standard models start feeling too conservative? That is a much more interesting problem than raw size. Because once the issue becomes growth, the black hole itself changes character. It is no longer simply a dark destination for matter. It becomes the final visible consequence of an invisible logistics system. Gas reservoirs, galactic collisions, radiative limits, feedback, instability, collapse, transport, time. The shining quasar is just the exposed surface. Beneath it lies a long, buried history of matter being delivered inward through conditions the universe no longer offers so generously. And that is why TON 618 feels less like an isolated wonder than a witness. A witness to an era when the cosmos could still build on a scale that now seems almost indecent. The younger the universe, the less emotional room we have for objects like this. And that shrinking room is exactly what makes TON 618 powerful. It corners intuition. It takes the oldest defense the mind has. There was plenty of time, and begins to remove it. Once that defense weakens, awe hardens into pressure. Now we are forced to ask not only how bright the quasar is, or how large the horizon might be, but what kind of machine could generate that brightness at all? Because a quasar is not the black hole itself. It is the wound the black hole opens in the matter around it. And to understand how a black hole becomes visible across 10 billion years of space and time, we have to look not into the darkness first, but into the inferno just outside it, the region where matter falls, compresses, overheats, and turns gravity into light. Because that inferno is the only reason TON 618 entered human awareness at all. If you could somehow remove the light, strip away the radiation, the glare, the superheated gas, the violent brilliance of everything still circling the abyss, the black hole itself would almost disappear from the story. Not physically. Gravitationally, it would remain what it is. But from across 10 billion years of space and time, there would be nothing for us to notice. No ancient beacon crossing the dark. No signature bright enough to force its way into our instruments. No reason, at first, to suspect that one of the most extreme gravitational systems ever measured was sitting there at all. TON 618 became visible because matter, before it vanished, was punished into light. That is what a quasar really is. Not a star, not a galaxy, not some exotic glowing object with a mysterious temperament. A quasar is the exposed violence of accretion. It is what happens when a supermassive black hole is not merely present, but actively feeding, when gas and dust do not pass cleanly into darkness, but are trapped first in a rotating structure so dense, so hot, and so fast that the region around the black hole can outshine the galaxy hosting it. The word itself has a strange history. When quasars were first identified, they looked almost like stars in the sky, compact, point-like, unnaturally bright. Their name originally came from that deceptive appearance, quasi-stellar radio source. They were tiny in image, immense in power. Even before the mechanism was fully understood, that mismatch was already a warning. Something about the universe had found a way to produce galaxy-level luminosity from a region too small, too concentrated, too intense to fit any comfortable category. TON 618 belongs to that lineage, but near its upper edge, where the mismatch becomes almost obscene. To understand why, it helps to be precise about what is happening around a feeding black hole, because this is one of those places where ordinary language quietly sabotages intuition. We imagine matter falling in, and the phrase makes it sound simple, like rain dropping through air, or a stone slipping into a well. But gas approaching a black hole almost never falls directly inward. It arrives carrying angular momentum. It is moving sideways as well as inward, and sideways motion matters. Because the closer matter gets to the black hole, the faster it must move to remain in orbit. So instead of plunging cleanly into darkness, the gas spreads into a disk. An accretion disk. That phrase sounds almost administrative, far too mild for what it names. In reality, this is one of the most violent luminous structures in the universe, a flattened whirl of plasma orbiting at enormous speed, with inner regions heated to temperatures so extreme that the gas radiates across the electromagnetic spectrum, visible light, ultraviolet, X-rays. The disk is not just hot, it is dynamically tortured. Different layers orbit at different velocities. Inner material races faster than outer material. Magnetic fields twist through the flow. Turbulence transfers angular momentum outward, allowing mass to spiral inward. Friction and shear convert ordered motion into heat. Gravity becomes light by first becoming punishment. And the crucial point is this: the black hole does not glow. The disk does. The horizon remains dark. The spectacle belongs to matter still outside it. Matter not yet lost. Matter in its final phase of visible existence. A black hole, in this sense, announces itself through what it is doing to everything near it. It does not shine from within. It shines by rearranging the fate of what approaches. A black hole shines brightest just before it erases the evidence. That is why quasars feel so psychologically unstable. They are luminous proof generated by disappearance. The thing creating the event cannot be seen directly. What we see instead is the cost paid by matter as gravity forces it through a narrowing corridor of heat, speed, compression, and no return. Now place that mechanism around a black hole with tens of billions of solar masses. The scale changes, but the deeper shock is not merely geometric, it is energetic. The gravitational well is so immense, and the supply of matter so enormous, that the accretion process can sustain luminosities almost beyond spoken usefulness. TON 618 is estimated to radiate with the output of roughly 140 trillion suns. That number is easy to say and almost impossible to feel. Human imagination starts to blur after a certain point. A trillion behaves more like a verbal signal of excess than a quantity the nervous system can hold. So it helps to return to mechanism. Why can a quasar become so bright at all? Because falling matter near a black hole can release energy with an efficiency that makes stars look surprisingly restrained. In the core of a star, fusion turns a small fraction of mass into energy. It is enough to power galaxies for billions of years. But accretion onto a black hole can extract much more from infalling matter before that matter is lost. Depending on the black hole's spin and the details of the flow, a substantial fraction of the material's rest mass energy can be radiated away. Not because the black hole is some magical cosmic lamp. but because gravity, when matter is forced into a deep enough well, becomes brutally good at converting motion into heat and heat into light. You could say a star shines because it is changing what matter is. A quasar shines because it is changing how matter dies. That is a severe distinction. And it matters because it explains why a black hole can become one of the most luminous, steady engines in the cosmos while remaining, in another sense, perfectly dark. The brightness is not a contradiction. It is the signature of matter being unable to arrive quietly. Even the geometry of the disk adds to the violence. The inner regions of the flow orbit so rapidly that relativistic effects begin to matter. Radiation pressure pushes outward while gravity drags inward. The plasma is dense with charged particles and threaded with magnetic instability. Some material is not swallowed at all, but flung outward in winds or collimated into jets that can travel vast distances, dumping energy back into the galaxy and beyond. So, the feeding process is not a neat one-way drain. It is an unstable bargain between inflow and resistance, between capture and expulsion, between collapse and feedback. And yet enough matter still reaches the center to keep the quasar blazing. That is the miracle, if one wants to use the word carefully. Not that the black hole exists, not even that it is enormous. The miracle, in the strictly physical sense, is that so much material can be organized into such an efficient, sustained radiative machine without the whole process choking itself off too quickly. Because light is not passive here, light pushes back. As matter falls inward and heats up, the emitted radiation exerts outward pressure. In principle, if the luminosity becomes too strong, that radiation can begin resisting the very inflow that powers it, push too hard, shine too violently, and the black hole's own feast should start to regulate itself. There is a kind of cosmic budget here, a tension between how fast matter can be supplied and how much radiative force the resulting light will use to fight further supply. Though that limit will become important. For now, what matters is the shape of the paradox we have entered. TON 618 is visible because matter around it is being driven through one of the most efficient energy release processes known in astrophysics. The quasar is not incidental ornamentation. It is the exposed surface of the engine. The light tells us that vast quantities of gas are not merely near the black hole, but being processed by it, accelerated, compressed, heated, and partially expelled on extraordinary scales. Which means the glow is not just spectacle, it is evidence. Evidence that the black hole is embedded in an environment capable of feeding it. Evidence that the accretion process is not a brief flash, but something sustained enough to be observed across cosmic history. Evidence that whatever made TON 618 so massive was not only ancient but organized. Somewhere in its unseen past, matter kept arriving. Momentum kept being shed, the engine kept receiving fuel. The brightness is the visible scar left by all of that hidden logistics. And once you understand that, the quasar stops being a pretty halo around a dark object and becomes something much more useful. A confession. The surrounding light is telling us, in the only language we can receive from so far away, that TON 618 is not resting on its mass like an inert monument. It is actively turning gravity into radiation on a scale that forces us to ask a harder question. Not just how such a black hole formed, how such a black hole was fed. Because a quasar this luminous does not merely require a monster at the center. It requires matter to keep arriving in enormous quantities. It requires a cosmic supply chain. It requires whole regions of a galaxy, perhaps more than a galaxy, to surrender material inward instead of using it all to make stars. And that means the visible blaze around TON 618 is already hinting at the next pressure point in the story. A black hole can shine like this only if it is eating. But the moment we start asking how much it must be eating, a new discomfort appears. For all its brilliance, even a monster this bright may still be growing more slowly than our intuition needs. More slowly than our intuition needs. Because luminosity and growth are not the same thing. They feel like they should be. That is another quiet trap in this subject. We hear that TON 618 shines with the output of something like 140 trillion suns, and the mind immediately tries to convert brightness into appetite. If it glows that hard, Surely it must be gaining mass at some unimaginable speed. Surely a black hole this luminous should be swelling almost explosively, as if light itself were proof of simple, limitless consumption. But the accounting is crueler than that. A quasar can be dazzling without making the growth problem disappear. To see why, we have to be a little more exact about what accretion is doing. Matter falling toward the black hole does not surrender all of itself to the horizon. A meaningful portion of the energy tied up in that infalling mass is radiated away first. That is what makes the disk so bright. The same efficiency that gives a quasar its terrifying luminosity also means some of the available mass energy is spent on light instead of being added directly to the black hole's weight. In other words, the blaze is not just evidence of feeding. It is evidence of cost. Every flood of radiation pouring out from the accretion disk is energy that came from somewhere. It came from the gravitational descent of matter. It came from gas surrendering orbital order, plunging deeper into the well, colliding, heating, glowing, resisting, and only then, only partially, being allowed to cross into the darkness. The black hole grows by what it keeps. The quasar shines by what the process burns off on the way. So, luminosity is not a simple measure of how much mass is being gained. It is a measure of how violently the gain is being negotiated. That distinction matters because when astronomers estimate the feeding rate for an object like TON 618, the result is enormous by any human standard and still, somehow, not emotionally enough. The numbers suggest that TON 618 may be accreting on the order of tens of solar masses per year, often quoted in the range of roughly 20 to 30 suns worth of material annually, depending on assumptions about efficiency and luminosity. That is an absurd rate. Entire stars' worth of matter being processed year after year, not by nuclear fusion, not by ordinary stellar collapse, but by a gravitational engine whose appetite is measured in suns per calendar cycle. And yet even that does not solve the real problem. Because 66 billion solar masses is a number so large that 20 or 30 more per year begins to look almost insultingly small against it. That is another one of the script's essential emotional reversals. The feeding rate sounds monstrous until the black hole's existing mass forces it into a different perspective. If you are a human being, 30 suns per year sounds like a cosmic emergency. If you are a black hole weighing tens of billions of suns, 30 more is not explosive growth. It is incremental, vast in local terms, modest in relative ones. The black hole eats stars by the year and still grows too slowly for comfort. That is not because the rate is unimpressive, it is because the timeline is vicious. If TON 618 were quietly adding a few dozen solar masses every year in the modern universe, with billions upon billions of years behind it, we could file the fact away under the category of grand but tolerable processes. But we are not dealing with a modern black hole at the calm end of history. We are looking back into a universe that had not been running for very long. So, the relevant question is not whether 20 or 30 solar masses per year is large in the abstract. It is whether rates like that, sustained over realistic periods, are enough to build a monster like this from plausible beginnings, before the available cosmic clock runs thin. And that is where brightness stops feeling reassuring. Because once the glow is translated into mass flow, and mass flow is translated into growth timescale, TON 618 begins to look less like a solved engine and more like a bookkeeping crisis. You can almost feel the equations turning against intuition. Yes, the quasar is brilliant. Yes, matter is pouring inward. Yes, the black hole is still gaining weight. But if it started from an ordinary stellar mass seed, the sort of black hole formed from the collapse of a massive early star, then even fierce feeding rates have a brutal amount of work to do. A few dozen solar masses per year sounds like avalanche growth until you ask it to produce tens of billions of solar masses on a young universe deadline. Then the glamour drains out of the number and the old anxiety returns. Was it really enough? This is where astrophysics becomes less about admiration and more about limits. There is a reason black hole growth is often discussed in relation to something called the Eddington limit, not because nature obeys it with perfect obedience in every circumstance, but because it captures a fundamental tension at the heart of accretion. As matter falls inward and lights up, the radiation it produces pushes outward on surrounding gas. The brighter the quasar, the stronger that radiative shove. At some point, luminosity begins to interfere with feeding, shine too powerfully, and you make it harder for fresh material to continue arriving. The black hole's brilliance becomes a partial enemy of its own hunger. That is a strangely human-seeming tragedy written into a non-human machine. To grow, it must feed. To feed efficiently, it must shine. To shine too much is to resist further feeding. The universe rarely offers pure advantages. Even its most violent engines carry brakes inside them. So, when we say TON 618 is one of the most luminous quasars ever observed, that statement does not simply tell us that the black hole was gorging itself. It tells us the system was operating near a dangerous tension point, where inflow and radiative resistance were locked in a difficult bargain. Some matter made it inward, some energy escaped, some gas was almost certainly blown back outward in winds. The disk was not a clean conveyor belt into darkness, it was a battlefield between capture and expulsion. And the more luminous the object, the more delicately that battlefield must be managed if growth is going to continue for long enough to matter. This is why the raw visual drama of quasars can be slightly misleading. The imagination sees the glare and assumes abundance solves everything. But from the black hole's point of view, radiance is not just triumph, it is leakage. It is mass energy not retained. It is proof that growth is happening under conditions of friction, resistance, and inefficiency. Even extraordinary feeding can leave a black hole historically behind if the seed was too small, the bright phase too brief, or the environmental supply too unstable. So, the light around TON 618 contains a hidden confession. Not only that the black hole is feeding, but that feeding alone may not explain its existence comfortably. Imagine trying to grow a colossal fortune while being forced to spend a large share of each income stream immediately, all while racing against a shrinking deadline. That is not a perfect analogy. Black holes are not bankers and galaxies are not economies. But it captures the feeling of the problem. The quasar's brilliance is part of what allows us to detect the object. It is also part of what prevents the growth story from becoming too easy. The very mechanism that reveals TON 618 also reminds us that the path to 66 billion solar masses is not as straightforward as, it was bright, therefore it grew. The brightness is not the answer. The brightness sharpens the question. Because if the black hole's current radiative power corresponds to a feeding rate that is immense but not infinitely accommodating, then we are forced to think historically. We have to ask what came before this visible phase. How massive was the seed? How often could growth proceed near or above the usual radiative limits? How much gas was available? For how long? Under what galactic conditions? How many interruptions occurred? How much of the mass came not from smooth feeding, but from mergers with other black holes brought together by colliding galaxies? All of those questions were already waiting beneath TON 618. The quasar light merely drags them into view. And now the object starts to become truly dangerous to intuition, because the more honestly we describe its present feeding, the harder it becomes to believe that ordinary growth, beginning from an ordinary start, can fully account for what we are seeing on the timescale available. Not impossible, perhaps. Physics does not hand us melodrama that cheaply, but uneasy, tight, constrained, the sort of situation where every assumption about initial conditions suddenly matters. This is where the black hole stops looking like an isolated monster and starts looking like the final visible outcome of a much earlier decision the universe made. Somewhere in the first chapters of cosmic history, the opening move may already have been more extreme than we once assumed. Because if a black hole this large was already roaring in the young universe, then perhaps the story did not begin with a small seed patiently climbing upward through ordinary feeding. Perhaps it began with something larger, much larger, or else the young universe found a way to feed black holes harder, faster, and with fewer breaks than our most comfortable models prefer to imagine. Or else the young universe found a way to violate our sense of gradualism without violating physics at all. That possibility is what makes TON 618 so much more than an extravagant black hole, Up to this point, the story could still be told as spectacle disciplined by mechanism. We began with the shock of scale. Then the light around the black hole forced us to talk about accretion, about energy, about the fact that matter does not simply fall into darkness, but is ground into radiation before it disappears. Then that same light betrayed a second truth. Brightness is not the same thing as easy growth. A quasar can look like excess while still hiding a historical shortage. It can blaze with absurd power and still leave us wondering whether the black hole had enough time to become what it already is. Now the tension tightens. Because once you stop staring at the glow and start doing the historical math, TON 618 begins to feel less like a marvel and more like a timing problem with teeth. At the center of that problem is a very simple question, almost naive in its wording and brutal in its consequences. What did this black hole start as? Every giant thing carries that question inside it. A mountain begins as uplift. A forest begins as seed. A galaxy begins as fluctuations in density so slight that they would have looked almost like nothing at all to any eye capable of seeing them. Black holes are no different. However titanic they become, they do not appear at full size. Somewhere there was a beginning. Somewhere gravity crossed a threshold and held. Somewhere a seed black hole formed. And once that seed exists, the rest of the story becomes a race between appetite and time. That is where the ordinary picture starts to strain. In the most conservative version of black hole growth, the first seeds are the remnants of massive early stars. A star forms from primordial gas, burns briefly, dies violently, and leaves behind a black hole maybe tens of times the sun's mass. From there, given enough surrounding matter, that seed can accrete. It can gain mass gradually. If galaxies merge, black holes can merge too. Over long enough timescales, small beginnings can become enormous endings. That story works beautifully for many parts of the universe. It is not obvious that it works comfortably here. Because a seed of a few dozen or even a few hundred solar masses is not merely smaller than TON 618. It is smaller by such an outrageous factor that every step of subsequent growth begins to matter with painful intensity. Every pause matters. Every feedback episode matters. Every period when gas is unavailable matters. Every time radiation pushes back too hard matters. Every time a galaxy fails to deliver material inward matters. Once the target is 66 billion solar masses and the available universe is still young, inefficiency becomes a kind of doom. This is why black hole growth is often described in terms of E-folding times, exponential gain, and Eddington-limited accretion. The language is dry, but the underlying drama is not. If a black hole accretes steadily near the Eddington rate, it can grow exponentially over time, each interval multiplying the mass rather than merely adding a fixed amount. That sounds generous, and in some sense, it is. Exponential growth is one of the few tools nature has for producing monsters in a hurry. But exponential growth only feels magical until you place it under a real clock. Then the miracle becomes conditional. How early does the seed appear? How often can it keep feeding near the limit? How much of that feeding is interrupted? How much mass is lost to radiation? How many mergers happen? How often is the environment favorable? How frequently does the young galaxy cooperate rather than starve its center? The moment you ask those questions seriously, black holes can grow fast, stop sounding like an answer, and start sounding like the beginning of a negotiation. And TON 618 is what that negotiation looks like when the demanded outcome is almost offensively large. We should be careful here. Objects like this do not prove that physics is broken. They do not force us into theatrical claims that everything we thought we knew has collapsed. The real tension is subtler, and therefore more interesting. TON 618 does not destroy the framework. It pressures the edges of it. It asks whether the initial conditions were heavier than we assumed, whether feeding episodes were more intense than our simplest models allow, whether certain galactic environments in the young universe were so rich in gas and so effective at delivering it inward that growth could remain close to its maximum pace for uncomfortably long spans. In other words, the black hole is not screaming that science has failed. It is whispering that our comfortable version of the story may be too gentle. That whisper matters because science often advances not when nature breaks the rules, but when nature obeys them more brutally than expected. TON 618 may be one of those cases. Imagine the young universe not as an empty stage slowly filling with structure, but as a crowded, unstable environment where gravity is working overtime. Gas is abundant. Galaxies are colliding. Turbulence is common. Angular momentum can be stripped away through mergers and instabilities. Dense reservoirs of material can be driven toward galactic centers. In such a universe, black holes do not merely wait for food. Some of them may sit at the bottoms of gravitational funnels, being fed by conditions that are difficult to sustain now, but were far less rare then. That begins to make TON 618 feel less like a freak accident and more like the upper extreme of an especially violent era. But still, there is a difference between an especially violent era and a black hole this large. The gap between those phrases is where the pressure lives. Because even if the early universe was rich in opportunity, the opening seed still matters. If you begin too small, the rest of the history has to work nearly perfectly. You need sustained accretion near the upper limit. You need access to immense gas supplies. You need relatively few long interruptions. You may need repeated mergers. You need luck, but not luck in the mystical sense, luck in the astrophysical sense, meaning a chain of favorable environments, favorable timings, favorable dynamics. The smaller the starting seed, the narrower the path becomes. And the narrower the path becomes, the more we begin to wonder whether the first black holes sometimes started larger than the ordinary stellar remnant picture allows. That possibility changes the emotional register of the story. Because once the seed becomes uncertain, we are no longer just looking at growth. We are looking at origins. We are no longer asking only how black holes fed. We are asking how the early universe chose to collapse. What kinds of structures formed before ordinary stars had time to dominate everything? Whether there were moments when enormous clouds of pristine gas, under the right conditions, skipped familiar stages and fell inward on a far more dramatic scale. This is where the script's real renewal point begins to emerge. Perhaps the universe did not climb all the way to TON 618 by patient increments from a small and ordinary seed. Perhaps it began with a leap. That idea is not fantasy. It grows out of a serious tension in astrophysics. The earliest known supermassive black holes already force scientists to consider whether some seeds were born heavy, not as the modest remnants of dying stars, but as the products of direct collapse, where huge clouds of gas in the early universe may have bypassed fragmentation and star formation, falling inward to create black hole seeds, thousands, tens of thousands, or even more massive than stellar remnants, not proven in every case, not settled into a neat consensus, but very much alive as a response to the timing pressure objects like this impose. The difference is enormous. Start with a seed of a few dozen solar masses, and growth to billions becomes a long, delicate climb. Start with a seed of 100,000 solar masses, and the climb is still brutal, but not absurd in quite the same way. The universe does not have to perform a miracle. It only has to begin more aggressively. And that is the profound shift TON 618 starts to force on us. The question is no longer just whether the black hole ate enough. The question becomes whether the young universe was willing to produce beginnings that already carried an extreme bias toward enormity. That thought is strangely unsettling because it means the violence may not have entered late. It may have been baked into the first move. The cosmos may have contained, very early on, the conditions for collapse on a scale we still instinctively reserve for the outcome, not the opening. We like growth stories because they preserve proportion. A seed, then a sapling, then a tree, a star, then a remnant, then a black hole, then a giant. TON 618 threatens that emotional order. It suggests that under the right ancient conditions, the universe may not always have respected such gentle sequencing. Some structures may have entered history already leaning toward excess. A black hole of this size does not merely test how fast nature can grow. It tests how extreme nature may have been willing to begin. And if that is true, then the next step in the descent is no longer about the quasar's light or even its present feeding rate. It is about the first seed in the dark, the one hidden moment when a young universe, still crowded with raw gas and unfinished galaxies, may have chosen collapse over patience and produced an opening mass large enough to make monsters like TON 618 historically possible at all. Because once you entertain that possibility, the entire atmosphere of the early universe changes. It is no longer enough to picture a young cosmos filled with stars, gas, and occasional black hole remnants quietly beginning their climb. That image is too orderly, too familiar. It treats the first great gravitational structures as scaled-up versions of processes we already understand emotionally: star formation, collapse, death, remnant, growth. It preserves sequence. It preserves proportion. It lets the mind believe that cosmic excess is something nature reaches only after long rehearsal. Heavy seed ideas threaten that comfort. They suggest that, under the right conditions, the universe may have been able to generate black holes that did not begin as small survivors of stellar death at all, but as the direct products of large-scale collapse, immense clouds of pristine gas falling inward so quickly, and under such unusual thermal conditions that they never fully fragmented into ordinary stars first. Instead of making a population of stars and then waiting for a few of those stars to die into black holes, the cloud might have skipped the patient route. Gravity might have taken the whole stage early. That is a very different opening move. Not because it breaks known physics. In fact, its power comes from the opposite. It is frightening precisely because it may be lawful. If the gas remains hot enough, if molecular hydrogen cooling is suppressed, if fragmentation is delayed, if angular momentum can be shed quickly enough, then the collapse may proceed on a scale far larger than the usual stellar remnant pathway permits. The result would not be a tidy little seed of a few dozen solar masses. It could be something vastly heavier from the start, a black hole seed already so large that later growth, while still demanding, no longer feels historically impossible in the same way. The universe does not need to cheat. It only needs to begin harder. And that line matters because it changes what TON 618 is doing to our imagination. The black hole no longer forces us to choose between ordinary growth and fantasy. It forces us to consider that the early cosmos may have contained channels of collapse that were rare, extreme, and yet entirely natural. Not miracles, not violations, just ancient conditions more severe than the modern universe usually offers. Try to picture the setting. No rocky planets, no settled spiral galaxies with long, quiet outskirts, no old, chemically enriched environments like the one that eventually produced our sun. The first great reservoirs of gas were simpler in composition, poorer in heavy elements, and therefore governed by a different thermal story. Cooling pathways that later helped gas fragment into many smaller clumps were not always available in the same way. Under certain circumstances, instead of breaking into a swarm of separate stars, an enormous gas cloud might remain comparatively coherent, dense, and hot, unstable on a much larger scale. Now imagine that cloud not as a mist drifting in emptiness, but as a structure under siege from gravity. It contracts, it heats, radiation struggles to leak out, angular momentum resists total inward fall, but instabilities redistribute it. The whole mass becomes less like a birthplace for many stars and more like a single argument for collapse. At that point, the emotional logic of the universe changes. We are used to nature building giants by accumulation. This is nature building giants by refusal, refusing to fragment, refusing to spread itself into many smaller futures, refusing patience. Under those conditions, the first step toward a monster like TON 618 may not have been a long climb from modest beginnings. It may have been a plunge. Perhaps the universe did not climb to TON 618. Perhaps it began with a fall large enough to make the rest of the climb survivable. That is the seduction of direct collapse thinking. It does not eliminate the growth problem, but it softens the starting wound. If you begin not with a 10 solar mass remnant, but with something tens of thousands or even 100,000 solar masses, the later history remains violent and demanding. But the arithmetic relaxes. Suddenly, the black hole's existence no longer requires such absurd fidelity to uninterrupted near-limit growth. The path is still narrow. It is simply less impossible looking. This matters because astrophysics is often shaped not by single solutions, but by reductions in pain. A model becomes attractive not because it makes every problem vanish, but because it removes the worst pressure from the system. Heavy seeds do that. They take the timing tension imposed by early ultramassive black holes and redistribute it backward into the conditions of the primordial universe. Instead of asking only, how did a tiny seed grow so impossibly fast, we begin asking, what environments in the early cosmos could produce a seed that was already extreme? That second question is richer. It ties black hole history to the physics of the first galaxies, to ultraviolet backgrounds that may suppress cooling, to turbulent inflows, to the strange chemistry of a universe before it had been enriched by repeated generations of stars, to halos massive enough to hold on to hot gas, to the possibility that some of the most important structures in cosmic history were shaped less by what formed and more by what failed to form. That last point deserves to sit for a moment. A heavy seed black hole may owe its existence not just to what the universe created, but to what it prevented fragmentation, prevented ordinary star formation from consuming the gas too early, prevented the cloud from resolving into 1,000 smaller destinies. Sometimes the path to a monster is not addition. It is the suppression of alternatives. That is one of the coldest truths in this story. Because it means TON 618 may trace part of its ancestry to absence, to stars that never formed, to branches of cosmic history cut off before they could diverge, to matter denied the chance to become anything gentler. The black hole, in that sense, may be the beneficiary of a very early concentration of fate. Still, direct collapse is not a completed victory speech. It is a serious idea under active investigation, not a decorative answer we can drop into the script and walk away from satisfied. The early universe was messy. Conditions for direct collapse were likely rare. The required suppression of cooling and fragmentation is delicate. Simulations show plausible pathways, but nature does not hand us clean laboratory controls at redshift 10 or 15. We infer, we model, we compare. We search for observational signatures that might distinguish heavy seeds from lighter stellar-born populations. There is evidence pointing toward the possibility. There is also room for debate over frequency, efficiency, and necessity. That uncertainty is not a weakness in the narrative. It is the narrative. Because TON 618 is not dangerous to thought, because it gives us a final answer. It is dangerous because it forces us to take certain answers seriously. The black hole pressures the opening chapters of structure formation. It reaches backward into the young universe and asks whether the first gravitational seeds were sometimes born in a mode more brutal than our gentler pictures prefer. And even if heavy seeds existed, they would not be enough by themselves. A large beginning is not the whole story. A seed of 100,000 solar masses is still a long way from 66 billion. The black hole would still need fuel. It would still need time, however compressed. It would still need a galactic environment willing to deliver matter inward. The direct collapse idea does not erase the rest of the puzzle. It only changes the altitude from which the fall begins. Which means the real power of this idea is not that it solves TON 618. It is that it changes the structure of the problem. The universe may not have been trying to grow monsters from tiny residues as often as we once assumed. In at least some regions, it may have prepared the board differently from the very beginning. It may have allowed black holes to enter history already advantaged, not omnipotent, not fully formed, but born with a head start so severe that later growth could become historically plausible rather than absurd. That is the midpoint turn hidden inside TON 618. The black hole is no longer just telling us about appetite. It is telling us about opening conditions. It is telling us that some of the most consequential objects in cosmic history may have been biased from birth by environments that rewarded concentration over diffusion, collapse over fragmentation, singularity over multitude. The younger the universe, the more those original conditions matter, because there has not yet been enough time for history to forgive a bad start. TON 618 looks less and less like an oversized endpoint. It begins to look like the survivor of an early cosmic advantage. But even that is only half the danger, because suppose the seed really was heavy. Suppose the young universe did occasionally permit these enormous direct collapse beginnings. Suppose gravity, chemistry, and radiation conspired to create black holes already leaning toward gigantism. That still leaves a second and equally disturbing possibility. The universe may not only have started some black holes large, it may also have fed them harder than the limits we usually treat as comfortable. Harder than the limits we usually treat as comfortable, because comfort is exactly what the Eddington picture was never designed to preserve. By now, the shape of the problem has changed. A small seed feels too fragile. A heavy seed feels plausible, maybe even necessary in some cases, but still incomplete, even if the young universe occasionally allowed direct collapse beginnings. A black hole does not reach tens of billions of solar masses on ancestry alone. It still has to feed. It still has to turn surrounding matter into growth. It still has to survive long enough and eat efficiently enough to carry that early advantage forward across a brutally short cosmic timetable. So the next pressure point appears almost automatically. What if the black hole did not only begin larger? What if, for critical stretches of its life, it also fed faster than the polite version of accretion history allows? This is where one of the most misunderstood ideas in black hole physics enters the story. The Eddington limit is often spoken of as though it were a cosmic speed limit written in stone, a hard boundary beyond which black holes simply cannot feed. That is not quite right. It is better understood as a balance point, a benchmark for when outward radiation pressure from luminous accretion becomes strong enough to counter the inward pull of gravity on ionized gas. If the system shines too intensely, the light itself begins to push infalling matter back. In its simplest form, the logic is elegant and harsh. The brighter the feeding process becomes, the more it sabotages itself. That is real physics. But real physics is not always tidy physics. Nature is rarely so courteous as to behave only in the cleanest idealized regime. The Eddington limit matters because it captures a central tension in luminous accretion. It does not matter because every black hole in every environment obeys it with perfect moderation at every moment of its life. Under certain conditions, especially in dense, chaotic, high-supply environments, accretion can become more complicated. The flow can thicken. Radiation can become trapped in the infalling gas rather than escaping freely. Geometry can stop behaving like the simple spherical thought experiments that make the classic limit feel so absolute. In those circumstances, the black hole may be able to ingest matter at rates that, in one sense or another, exceed the standard Eddington picture for meaningful intervals. Not forever, not without resistance, not as a license for infinite appetite, but long enough to matter. And long enough to matter is precisely the kind of phrase Ton 618 forces us to take seriously. Try to picture what super Eddington accretion really means. Stripped of the abstract label, matter is arriving so aggressively, in such thick and luminous flows, that the usual bargain between gravity and radiative push becomes less clean. Photons generated deep in the inflow do not escape efficiently. They are dragged, scattered, trapped, advected inward with the gas. The system is still bright, often immensely bright, but the radiation does not oppose the incoming material as effectively as a cleaner, thinner disk would. Some of the energy that might have become a perfect braking force remains entangled with the very matter the black hole is trying to consume. The light is still fighting back. It is just no longer fighting under ideal conditions. That subtle failure of escape can become historically decisive. Because the growth problem posed by early giant black holes is not asking for magic. It is asking for episodes, intervals, windows of time where the universe allowed feeding to remain unusually intense. If a black hole can spend even portions of its life accreting above the gentle textbook pace we instinctively treat as normal, then the arithmetic changes. Not infinitely, not enough to erase every difficulty, but enough to make the climb toward extremity less absurdly narrow. This is one of the quiet themes running underneath the whole story. Nature does not always need a single dramatic loophole. Sometimes it needs several moderate ruthlessnesses layered on top of one another. A heavy seed, a dense environment, repeated merger activity, and, perhaps, bursts of accretion in which the usual radiative breaks were partially bypassed by geometry, density, or photon trapping. None of those by itself may be sufficient. Together, they begin to sound like an era rather than an exception. That is what makes the young universe feel less like a backdrop and more like an accomplice. In the modern cosmos, gas supplies are thinner, galaxies more settled, collisions less common, and many central black holes relatively subdued. The universe now is older, more structured, in some ways more mature, and less willing to funnel huge reservoirs of matter directly toward galactic centers. But in the quasar era, the great age of black hole feeding, conditions were uglier in exactly the right way. Gas was abundant, mergers were frequent, instabilities could drive material inward with a force that no calm spiral galaxy is eager to reproduce today. Under those conditions, the phrase super Eddington stops sounding like an exotic loophole and starts sounding like something the universe might occasionally stumble into, simply because the supply was too violent for elegance. A black hole does not need to behave recklessly forever. It only needs a few eras of recklessness early enough to matter. And that line carries a very specific emotional sting because it breaks another intuition we like to preserve. The idea that the universe's largest structures are always the product of dignified, stately growth. TON 618 keeps pushing us toward a less comfortable picture. Maybe some giants were not built by long patience alone. Maybe they were built through phases where matter arrived too quickly, too thickly, too continuously for the usual self-regulating neatness to keep up. The black hole's history may not have been graceful. It may have been crowded. This possibility also reframes the meaning of the quasar light itself. Earlier, the luminosity seemed like both a confession and a complication, evidence of immense feeding, but also a reminder that radiation wastes some of the mass energy and pushes back against the inflow. Now that same luminosity acquires a second layer. In some regimes, the light may no longer be a perfect obstacle. The system can become so optically thick, so geometrically swollen, that the outward force of radiation is partly trapped inside the inflow rather than cleanly unleashed against it. The black hole is not violating the laws of feedback. It is exploiting their messier implementations. Physics remains lawful. Lawfulness simply turns out to be more permissive, under pressure, than comfort would prefer. That is one of the deepest reasons objects like TON 618 are so destabilizing. They do not force us into fantasy. They force us into realism at higher stress. The equations do not suddenly become mystical. They become less psychologically convenient. We start discovering that the universe may have had multiple ways to be extreme while still remaining perfectly within its own rules. And yet it is important not to overstate this. Super Eddington growth is not a universal solvent. It does not let every tiny seed become a monster on command. Sustaining such phases is difficult. Feedback still matters. Outflows can still carry mass away. Gas supplies can still become chaotic or exhausted. Observationally and theoretically, the details remain active terrain. How often such episodes occurred, how long they lasted, how strongly they contributed to the rise of the earliest supermassive black holes, and under which environments they became decisive rather than incidental. That uncertainty is not a defect in the narrative. It is the source of its pressure. Because TON 618 does not ask us to pick one elegant answer and relax. It forces us to think in combinations. Perhaps some early black holes began heavy. Perhaps some fed above the gentler benchmark for meaningful spans. Perhaps some galaxies delivered gas inward with unusual persistence. Perhaps mergers stitched multiple lines of growth together. The black hole becomes the final visible result of a sequence in which several uncomfortable possibilities do not need to be absolute. They only need to overlap. That overlap is what history feels like when it becomes too efficient. And once you see that, the whole emotional register of TON 618 shifts again. The black hole no longer looks like a single impossible appetite at the center of space. It begins to resemble a cumulative victory by the early universe over every assumption that should have slowed it down. Small seeds may have been replaced by heavy ones. Radiative caution may have been punctured by dense inflows. Time may have been short, but the conditions were more ruthless than our intuition was prepared to grant. The universe did not have to choose one way to exceed expectation. It may have chosen several at once. That is when the object stops feeling like a statistical oddity and starts feeling like the upper visible tip of a much larger system of support. If a black hole can become this massive, this luminous, this early, then it is almost certainly not acting alone in any meaningful sense. It is being served by its surroundings, by a host galaxy, or repeated hosts, by merger history, by gas reservoirs, by gravitational torques, by the architecture of an entire region willing to feed the center instead of letting that matter remain comfortably distributed. In other words, the next descent is no longer about the black hole in isolation. It is about the cosmic supply network around it. Because a monster like this is not merely born and not merely hungry. It has to be delivered. That is the point where TON 618 stops behaving like an isolated object and starts behaving like the visible mouth of a much larger machine. Up to now, we have been following a sequence the mind can still, with effort, picture locally. A black hole, an accretion disk, a feeding rate, a seed, a timeline. Even when the numbers become absurd, the imagination keeps trying to shrink the drama back down to a central engine, a monster in one place doing monstrous things. But black holes do not generate their own food. They inherit it. Every atom crossing that horizon had to come from somewhere. Every flare of luminosity around TON 618 implies matter that was once farther out, colder, less committed to destruction, gas that might have remained diffuse, gas that might have formed stars, gas that might have settled into quieter structures. Instead, enormous quantities of it were transported inward, stripped of angular momentum, funneled toward the center, and converted into one of the brightest sustained engines in the universe. That does not happen because a black hole is impressive. It happens because an entire environment becomes complicit. This is where the galaxy surrounding a quasar ceases to be background scenery and becomes part of the mechanism. A black hole can only eat what its surroundings are willing, or forced, to surrender. In calm galaxies, that surrender is limited. Gas forms stars in the disk. Clouds orbit without falling all the way to the center. Angular momentum protects matter from immediate capture. A galaxy can hold enormous reservoirs of material without simply dumping them into its central black hole. In fact, most galaxies do exactly that. Their central black holes exist, but they are not blazing like quasars. They are underfed, intermittent, relatively quiet. TON 618 belongs to a different class of history. The black hole is not merely living in a galaxy. It is sitting at the bottom of a logistical catastrophe. Something, or more likely many things at once, had to keep driving material inward. Gas-rich mergers, gravitational instabilities in the host, tidal torques, dense inflows from a chaotic intergalactic environment, repeated disruptions that robbed matter of the one thing it needed to remain safely distributed, rotational order. The farther from the center you begin, the harder it is to fall inward cleanly. Matter wants to orbit. It wants to preserve its motion. It wants to avoid surrender. To get it all the way down into the feeding zone of a supermassive black hole, the galaxy must become a system that does violence not just to matter, but to the structure of its motion. Angular momentum is the quiet protector of ordinary cosmic life. To grow a monster, that protection has to fail. That is why the phrase feeding a black hole is almost too soft. It sounds like provision, a kind of passive nourishment. What is actually happening is transport on a violent scale. Clouds collide, gas shocks, bars and instabilities in galactic structure drive material inward. Mergers disturb orbits and deepen central potentials. The architecture of the galaxy itself becomes less like a stable home for stars, and more like a machine for concentrating fuel where it is most dangerous. At this scale, gravity stops looking like attraction and starts looking like infrastructure. That line is more literal than it sounds, because what TON 618 likely required was not just a large stockpile of gas, but a multi-stage delivery chain. Matter from large galactic radii must move inward to smaller radii, then smaller radii to smaller still. Each stage requires a different kind of transport problem to be solved. It is not enough for a galaxy to be rich. It must be dynamically willing to give up its richness. It must repeatedly fail to keep matter spread out. It must, in effect, become bad at remaining a galaxy in the ordinary, balanced sense. Quasars are often brightest when galaxies are least emotionally legible. That is part of their violence. They belong to phases when the host is not serene, not settled, not a finished civic arrangement of stars orbiting in neat obedience. It is under pressure. Star formation may be surging. Collisions may be ongoing or recent. Gas densities may be extreme. The central regions may be dense, turbulent, unstable. A quasar that bright is not just telling us there is a black hole at the center. It is telling us the entire host system is in a state where centralization has won. And centralization is never free. If huge amounts of gas are being driven inward, then less of that gas is remaining available for gentler futures. Some of it still forms stars, of course. Quasar hosts are not sterile environments, but there is competition now between stellar birth and black hole feeding, between distributed luminosity and centralized appetite. The galaxy is not just a container around the black hole. It is a contested landscape in which matter is being asked what it will become. A star, a disk, a cold cloud, a quiet orbit, or fuel. TON 618 suggests that, for long enough, an astonishing fraction of that answer was fuel. This is one reason the most luminous quasars feel so severe. Their existence implies not just abundance, but successful concentration. The universe did not merely place enough matter in the same general neighborhood. It delivered that matter inward through multiple barriers that ordinarily keep galaxies from surrendering their mass too efficiently to the center. A quasar of this scale is therefore not just a beacon of black hole power. It is a fossil record of organizational success. If one can use the word success for a process that may leave galaxies heated, disrupted, and partially stripped by their own central engine. Because the black hole is not a passive beneficiary of this arrangement. It feeds back. That is the next cold turn in the story. As gas falls inward and the quasar lights up, the released energy does not simply vanish into space as harmless spectacle. Radiation pushes on surrounding material. Winds can be launched. Jets, if present, can inject energy far beyond the core. Gas can be heated, stirred, expelled, or prevented from cooling. In other words, the black hole being fed by the galaxy can begin altering the galaxy's future capacity to feed it. The feast starts sabotaging its own supply lines. That is one of the great ironies of black hole growth at the highest scales. A quasar is evidence that matter is reaching the center. It is also evidence that the center may be trying, with tremendous power, to blow some of that matter back out. The black hole becomes both sink and disruption, both destination and source of galactic weather. It consumes the host's generosity and then punishes the host for being generous. A galaxy can spend millions of years building a monster and then be scorched by the result. So, when we look at TON 618 and talk about its mass, its event horizon, its luminosity, we are not just discussing a black hole. We are discussing a period in which an entire galactic ecosystem may have been organized around inward delivery, while simultaneously being transformed by the violence of that delivery. The central engine is no longer local. Its consequences leak outward. Star formation can be regulated. Gas can be redistributed or removed. The host can be reshaped by the very object it helped enlarge. That feedback matters historically because it means the growth of a monster black hole cannot continue indefinitely in the same mode. There may be bursts, interruptions, reignitions, periods of efficient feeding followed by self-inflicted scarcity, phases where mergers or fresh inflows restore the supply. The history becomes episodic, not smooth, a sequence of violent opportunities separated by the black hole's own attempts to sterilize its environment, which only deepens the logistical miracle. TON 618 is not just a black hole that once found food. It is a black hole that found enough food, often enough, in a universe capable of repeatedly rebuilding or maintaining the channels that delivered it. That is a much harder story to tell than "it was very hungry." It was served, And once you say that honestly, the scale of the support system becomes almost more disturbing than the scale of the black hole itself. Whole galactic structures may have functioned, for critical stretches of cosmic time, as delivery mechanisms for a center that would eventually radiate with the power of 140 trillion suns. Mergers were not just dramatic events. They may have been shipments. Dense gas reservoirs were not just raw material for star formation. They were potential installments in a long gravitational transfer. The host galaxy was not simply home. It was a supply chain under pressure. That pressure also tells us something more general about the quasar era. TON 618 may be extreme, but it is not floating outside history. It belongs to a period when black holes and galaxies were growing together under unusually violent conditions. That does not make every quasar a future TON 618, but it does mean that, to understand the monster, we cannot treat it as detached from its age. The black hole's excess is partly the universe's excess. Its hunger is partly the era's abundance. Its luminosity is partly the visible confession of a time when galaxies were more gas-rich, more collision-prone, and more willing to funnel matter inward than the calmer cosmos around us now. The monster is not isolated. It is historical, and that changes the feeling of the whole object again. TON 618 is no longer merely a giant black hole that somehow happened. It becomes the center of a rare but lawful convergence, a heavy or fast-growing seed, a supply-rich host, repeated inward transport, and an era of cosmic history permissive enough to let all those advantages overlap. That convergence is already difficult enough to believe. The next difficulty is worse, because even if a galaxy is willing to serve a monster, and even if the young universe occasionally makes such service possible, we still have to face one last demand before the story can hold. We have to trust that the mass we are talking about, 66 billion suns, is not an illusion of distance, brightness, or our own interpretive hunger. We have to ask what, exactly, it means to weigh darkness from 10 billion years away. We have to ask that because TON 618 is too distant, too ancient, and too overwhelming an object to tolerate casual numbers. When people hear that a black hole weighs around 66 billion suns, the figure can sound like one more extravagant claim in a subject already crowded with extravagant claims. Black holes are always huge. Quasars are always bright. Distances are always absurd. At some point, the imagination goes numb, and numbness is dangerous, because it makes the estimate feel arbitrary, as if astronomers pointed a telescope into the dark, saw a brilliant point of light, and attached an incomprehensible mass to it by tradition, confidence, or taste. That is not what happens. But it is also true that we do not weigh an object like TON 618 the way we weigh a planet, a star, or even the black hole at the center of our own galaxy, Sagittarius. A star is close enough that we can literally track stars whipping around the unseen center of the Milky Way and infer the mass from orbital motion. There, the measurement has a certain brutal intimacy. You watch the stars bend. You watch the clockwork tighten. Gravity leaves fingerprints on individual trajectories. TON 618 offers no such kindness. It lives so far away that the host galaxy is not a clean stage on which we can watch stellar orbits one by one. What reaches us is the quasar, the central radiative engine so bright it overwhelms much of the surrounding structure. We do not stand beside it and take inventory. We reconstruct it from light, from motion encoded in light, from timing, from spectral width, from the behavior of gas under a gravitational regime too remote to witness directly. We do not see the black hole itself, and we weigh it by the obedience of light to gravity. That distinction matters because it gives the measurement both its authority and its uncertainty. The mass of TON 618 is not a guess in the childish sense. It is an inference built from physically meaningful quantities. But like many of the most impressive measurements in astronomy, it is an inference that depends on models, assumptions, and calibration against other systems where the geometry is kinder. The basic logic begins with the broad line region, gas moving at high velocity, relatively close to the black hole, close enough that its motion is strongly governed by the central mass, but far enough out that it still radiates spectral lines we can observe. That gas is not moving randomly. It is trapped in the black hole's gravitational influence, orbiting or circulating in a deep central potential. The faster it moves, the stronger the gravity must be. That much is intuitive. And motion can be read from light. When gas moves rapidly, the spectral lines associated with its atoms are broadened by the Doppler effect. Material moving toward us shifts the light one way. Material moving away shifts it another. In a violently moving cloud ensemble around a black hole, the result is not a sharp, clean line, but a broadened one, a spectral smear that carries, hidden inside its width, the characteristic speeds of the gas. Very broad lines imply very fast motion. Very fast motion implies a very deep potential. A very deep potential well, if the gas is gravitationally bound, implies a very large central mass. So one ingredient is velocity. But velocity alone is not enough. You also need scale. You need to know, at least approximately, how far that gas is from the black hole. A car moving very fast around a small circle tells you something different from a car moving the same speed around a much larger one. The same is true here. Gas speed by itself does not uniquely determine mass. You need the radius of the orbiting or emitting region as well. And that is where one of the most elegant techniques in observational astrophysics enters: reverberation mapping. The phrase sounds clinical. The reality is almost intimate. The central accretion disk varies in brightness over time. Those variations travel outward as changes in illumination. Gas farther out in the broad line region responds after a delay, because light takes time to cross the intervening distance. Measure that lag carefully enough, and you gain an estimate of the characteristic size of the line-emitting region. In effect, the quasar flashes, the surrounding gas answers, and the pause between those two events becomes a ruler. It is one of the strangest measuring tools science has ever made. You weigh darkness by timing echoes of light. Once you have an estimate of the gas velocity from line broadening and an estimate of distance from reverberation or related scaling relations, you can invoke the virial logic of gravity. Faster motion at a given radius requires more mass. From there comes the black hole estimate. In practice, for extremely distant quasars like TON 618, astronomers often rely not on full reverberation mapping campaigns alone, which are observationally demanding, but on relationships calibrated using nearer active galaxies where the geometry can be constrained more directly. Luminosity correlates statistically with the size of the broadline region. Line widths provide velocities. Together, they yield a mass estimate. It is a chain of reasoning grounded in physics, but still a chain, not a single perfect glance into truth. That is why the number deserves both trust and humility. Trust, because it is not decorative. It emerges from measurable properties of the quasar's light that encode gravity in a disciplined way. Humility, because broadline geometry is not always simple. Is the gas in a disk a more chaotic distribution? Inclined at what angle? How much do radiation pressure, outflows, or non-virial motions complicate the interpretation? How universal are the scaling relations at the most extreme luminous end? These are not trivial questions. Different assumptions can move the mass estimate. Error bars are real. Extremes are hard. Nature becomes harder to calibrate precisely when it is least interested in behaving moderately. But uncertainty is not the same thing as collapse. This is one of the most important discipline points in a script like this. The honest story is not that TON 618 might secretly be small, and astronomers have no idea what they are talking about. The honest story is that even allowing for uncertainties, TON 618 remains an ultramassive black hole of extraordinary scale. Perhaps the exact number shifts somewhat, depending on method and assumptions. Perhaps the central estimate carries more ambiguity than a close, orbit-based measurement would. None of that rescues intuition. None of it turns the black hole into something ordinary. The uncertainties live around the summit, not down at sea level. And that is almost more unsettling. Because what science offers us here is not absolute theatrical certainty, but something colder, a remote object so luminous, so broad-lined, so gravitationally deep that even conservative inferential methods still place it among the heaviest black holes ever seriously discussed. The details can breathe. The extremity remains. There is also a secondary consistency check buried in the quasar's brightness. If the luminosity is roughly known, and if the black hole is not wildly violating the expected balance between radiation and gravity, then the inferred mass and the quasar's output can be compared for plausibility. A quasar of this brilliance requires a central engine capable of sustaining it without becoming physically absurd under ordinary active galaxy assumptions. In that sense, the light is not only the thing being interpreted, it also helps police the interpretation. The estimate is not floating free. It sits inside a network of mutually constraining facts: luminosity, line widths, radius estimates, accretion logic, and the known behavior of active galactic nuclei. The mass is inferred, but it is not invented. This matters emotionally because once the measurement begins to feel real, the whole story hardens. Before that, TON 618 can still be treated as a mythic exaggeration, one more huge number used to provoke cosmic vertigo. After the weighing logic is understood, even at this distance, the object becomes less like a story and more like a verdict. The quasar is not simply bright. It is moving gas in ways that require a central gravity well of staggering scale. The evidence is indirect, yes, but so is much of our knowledge of the deep universe. Indirect does not mean weak. Sometimes it means the universe is too far away to touch. So we learn to touch it through disciplined traces. Astronomy is full of that kind of dignity. We measure what cannot be held by reading what it changes. And once the mass estimate survives that scrutiny, the black hole becomes stranger again. Because 66 billion suns is not just a statistic about how much matter sits behind a horizon. It is a statement about geometry, about curvature, about the structure of space and time in the presence of a gravity well so large that even its event horizon expands beyond the scale of our planetary system. Up to this point, TON 618 has been a historical problem, a growth problem, a feeding problem, a galactic logistics problem, and an observational inference problem. Now it becomes something else. Now we have to face what a black hole this large actually means as a place. Not in the poetic sense, in the physical one. Because the next surprise is that the closer you get to an ultra-massive black hole, the less it resembles the violent cartoon most people carry in their heads. The deepest strangeness is no longer the appetite. It is the geometry. It is the geometry, because by the time a black hole becomes this large, violence stops behaving in the way popular imagination expects. Most people picture a black hole as a place of immediate destruction, a narrow cosmic trap where anything approaching too closely is shredded, crushed, and torn apart in some spectacular act of gravitational cruelty. The image is not entirely wrong. Black holes can certainly destroy. Tidal forces can rip stars into streams of incandescent debris. Matter in the accretion flow can be heated to temperatures that would erase any familiar form of structure. Near the end of the story, no known material object survives. But there is a subtler truth here, and in TON 618 it becomes almost unnervingly clear. The larger the black hole, the stranger the horizon becomes. Not because the event horizon gets less real. It remains exactly what general relativity says it is, the boundary beyond which no signal can escape to the outside universe. But because the local experience of approaching that boundary depends strongly on the black hole's mass. For a stellar mass black hole, tidal forces near the horizon can be catastrophic. The difference in gravity between your feet and your head becomes so extreme, so quickly, that the old phrase spaghettification is more than a metaphor. Space itself imposes a gradient your body could never negotiate. With an ultramassive black hole, the numbers change. Dramatically. Because the event horizon lies so far from the center, stretched outward over a truly enormous radius, the gravitational gradient right at that boundary can be much gentler than intuition expects. Not gentle in any ordinary human sense. Not safe in the larger context of the environment. A quasar like TON 618 is surrounded by radiation, plasma, magnetic violence, and orbital energies that would make survival a fantasy long before any horizon crossing. But if you imagine, in the abstract, a clean approach to the event horizon itself, the horizon of a sufficiently massive black hole is not necessarily the place where local physics suddenly explodes in your face. That is one of the most disorienting facts in the subject. The event horizon is not a wall. It is not a surface. It is not a physical membrane waiting to be struck. It is a geometric threshold, and geometry is colder than impact. This is where everyday intuition begins to fail in a more serious way. We are built to understand boundaries as visible things: doors, cliffs, skin, coastlines, the edge of a table, places where contact changes. But the event horizon is not like that. If you were somehow falling freely toward a non-rotating black hole and had the miraculous protection needed to survive the surrounding environment, you would not, in your own local frame, feel yourself hit a border when you cross the horizon. There would be no cosmic alarm, no flash announcing the moment, no visible line hanging in space. The threshold is real not because it feels like something, but because it changes what futures are physically available. Outside the horizon, there exist trajectories, at least in principle, that lead back outward. Inside the horizon, all future-directed paths lead deeper in. That is an extraordinary sentence to say about reality. Inside a black hole, the problem is no longer simply that escape is hard. Escape stops being a future option. This is one of the great achievements of general relativity. It takes what sounds like a dramatic prison and reveals it to be a statement about space-time itself. A black hole is not merely pulling on things with brute force. It is altering the geometry through which all motion, all causality, all possible futures must pass. Near the horizon, inward begins to stop acting like a direction you can choose to avoid. It becomes more like a destination written into the structure of time. The event horizon is a change in what the future is allowed to mean. That line matters because it transforms the black hole from an astrophysical object into an ontological disturbance. We are no longer just talking about a massive thing with a strong pull. We are talking about a region where the architecture of space-time has been curved so deeply that the distinction between movement and inevitability starts to blur. The larger the black hole, the easier it is to see this with a kind of severe clarity, because the horizon is no longer hiding inside a tiny compact scale where popular images of ripping and tearing dominate every thought. It expands outward enough for the geometric nature of the threshold to become the main event. And TON 618, with its immense mass, drives that point almost mercilessly. Its Schwarzschild radius, the characteristic size of the event horizon for a non-rotating black hole of equivalent mass, extends across a realm so vast that our solar system becomes the nearest emotional comparison available, even though that comparison is already straining. At that scale, the horizon is not some tiny, dense bead hidden inside a stellar corpse. It is a region of space-time so extended that the very phrase approaching the black hole changes meaning. You are not converging on a sharp point in the ordinary sense. You are entering a vast geometry whose consequences become irreversible long before they become visually intuitive. This also changes how the black hole would appear to distant observers. General relativity predicts that clocks deeper in a gravitational well run differently relative to clocks farther out. Signals climbing away from strong gravity are redshifted. Time near the horizon appears increasingly slowed from the perspective of a distant watcher. To someone safely far away, an infalling object seems to fade, redden, and asymptotically linger near the horizon, never quite crossing in any visually straightforward sense. But for the falling object itself, proper time continues. The crossing happens. No infinite pause is experienced locally. Two accounts of the same event coexist, each true within its own frame, and neither especially interested in making human intuition comfortable. That is not just technical oddness. It is a direct insult to the way the mind expects a single event to behave. We want one clean story. Did it cross or not? Did time slow or not? Is the boundary there or not? Black holes answer with a geometry that allows all those questions to survive, but only if we surrender the demand that our everyday categories remain globally valid. Reality does not become contradictory. It becomes less provincially narrated. Even the famous point of no return phrase, useful as it is, risks sounding more dramatic and less precise than the truth. A point of no return suggests a location where one still meaningfully could turn around until a final opportunity is missed. The horizon is subtler. It is not the moment a door slams. It is the place beyond which no outward-directed future exists. That may sound like philosophy wearing a physics costume. It is not. It is what the equations say about causal structure in curved spacetime. And because TON 618 is so large, the conceptual purity of that statement becomes harder to ignore. The horizon is not the violent ending people imagine first. It is a lawful rearrangement of possibility. Only later, deeper in, does violence become unavoidable in the more intuitive sense. This is also where black holes begin to reveal something almost cruel about human perception. We evolved to understand force, impact, collision, visible motion, local surfaces. We did not evolve to understand metric structure. We did not evolve to feel curved spacetime as such. So, when reality organizes itself through geometry rather than contact, our instincts lag badly behind. We keep reaching for images of sucking, crushing, swallowing, all emotionally vivid, all partly misleading. The more accurate image is quieter and therefore more unnerving. A region of the universe where the shape of space-time itself that has been altered so completely that ordinary distinctions between path and fate start collapsing into one another. TON 618 sharpens that lesson because it is too large to dismiss as a specialized oddity. It is geometry with planetary system scale, geometry so vast that the threshold of irreversibility would engulf the familiar map of our own neighborhood. Geometry built not in a mathematical notebook, but by the concentration of 66 billion suns into one gravitational fact. And once we accept that, the black hole grows stranger again. It is no longer only a giant engine of accretion, nor only a historical puzzle about early growth, nor only a galactic sink fed by violent logistics. It becomes one of the clearest natural demonstrations that space and time are not passive containers in which matter acts. Matter tells geometry what to do. Geometry tells matter how to move. At TON 618 scales, that relationship stops feeling like an elegant slogan from relativity and starts feeling like a physical assault on ordinary thought. The black hole does not sit inside spacetime like a heavy object dropped into a box. It rewrites the box. And that brings us to the next threshold in the descent, because if the horizon is already this strange, if it is not a wall but a causal boundary, not an impact but a restructuring of the future, then the real terror of the black hole lies even deeper, beyond the accretion light, beyond the event horizon, beyond the point where intuition fails gracefully. Somewhere further in, the equations themselves begin to lose their right to certainty. That is where the black hole stops being merely hard to imagine. That is where it becomes a limit of theory. That is where the black hole becomes more than an extreme astrophysical object. It becomes a place where our best description of reality begins to consume itself. Up to the event horizon, general relativity remains unnervingly coherent. Strange, yes. Hostile to intuition, certainly, but coherent. The equations continue to tell a lawful story. Space-time curves, light bends, clocks diverge, futures narrow. Horizons emerge. None of that is comfortable, but it is still physics behaving like physics, severe, elegant, and structurally intact. The singularity is different. The singularity is not simply the center of the black hole in the ordinary geometric sense, like the center of a sphere or the middle of a city. It is the place where the mathematical description given by classical general relativity stops producing finite, physically interpretable answers. Curvature grows without bound. Density, in the idealized equations, ceases to remain a quantity the mind can meaningfully compare to anything else. The theory does not calmly complete the picture. It drives it toward a kind of formal catastrophe. That is why the singularity matters so much, and why it is so often misunderstood. It is not terrifying merely because it sounds dense. It is terrifying because it signals the breakdown of the current language. When people speak casually about the singularity as though it were a literal, infinitely small point containing all the mass, they often smuggle in more confidence than physics has really earned. Infinity inside an equation is not always a thing waiting patiently in nature to be photographed. Sometimes it is a warning flare, a signal that the theoretical framework has reached the edge of its competence. General relativity is one of the most successful physical theories ever written. It predicts black holes, gravitational lensing, time dilation, gravitational waves, all with astonishing precision. But at the singularity, its victory becomes too complete. Curvature does not become merely large. It becomes unbounded. The theory does not hand us a final object. It hands us an admission that something deeper is required. The singularity is not where knowledge ends. It is where our present grammar for reality fails. That is a more serious kind of unease than any popular image of destruction. It means that, at the deepest interior of one of the most lawful structures in the cosmos, lawfulness, at least as currently formulated, ceases to remain enough. Not because the universe has become irrational, because our description has become incomplete. This is where black holes stop being only about gravity and start becoming about reconciliation. General relativity governs the large-scale structure of spacetime. Quantum theory governs the small-scale behavior of matter, fields, uncertainty, and information. Both are triumphs, both are indispensable. But in the deepest interior of a black hole, and in the earliest moments of the universe itself, the two are forced into the same room. Extreme curvature, extreme density, extreme short-distance physics. And that is precisely where our current frameworks refuse to merge cleanly. TON 618 does not just dramatize largeness. It dramatizes unfinished unification. Because once you follow its logic all the way inward, the black hole becomes a monument to a fact physicists have lived with for generations. Our most successful theories are magnificent, but not yet whole together. At a certain depth, the mathematics of spacetime and the mathematics of the quantum world both insist on relevance, and our current ability to make them speak one language remains incomplete. That is not an embarrassment. It is one of the deepest truths science has ever reached, honestly. There is a temptation, in narrating black holes, to turn this into mystical fog, to say the singularity is a place beyond science, a cosmic secret forever inaccessible, a poetic abyss where reason dissolves into awe. That is elegant language, and most of it is too lazy. The real situation is harder and more dignified. The singularity is not beyond science. It is exactly the kind of place that tells science where its next work begins. It is not an invitation to surrender rigor. It is a pressure point demanding a deeper rigor than we currently possess. Black holes are not failures of physics. They are places where successful physics exposes its own incompletion. That distinction matters because it keeps the tension honest. We are not standing at the edge of magic. We are standing at the edge of unfinished understanding. There may be no literal singularity in the final theory. Quantum gravity, whatever its final form, may replace the classical divergence with something more structured, more finite, more lawful at small scales. Different approaches suggest different possibilities. Quantum-corrected cores, fuzzball-like constructions in some string-inspired pictures, bounce scenarios, emergent space-time descriptions, holographic frameworks in which the deepest interior is related in subtle ways to boundary information. None of these have earned the right to be narrated as settled truth, but all of them testify to the same pressure. Infinity in the classical equations is unlikely to be the final word. And that returns us to TON 618 with an unexpected sharpness. Because a black hole this large does not only expand the scale of the horizon, it expands the emotional mismatch between what the universe can build and what the human mind is equipped to hold as one coherent thing. At one level, TON 618 is a physical object with a gravitational field, a feeding history, a host environment, and measurable mass. At another, it is a doorway into one of the deepest unresolved problems in theoretical physics. The The same structure that can be weighed from spectral lines eventually leads us to a place where our current theories stop agreeing on how reality should behave. There is something almost indecent about that. An object can be observationally real and theoretically terminal at the same time. That is the black hole condition. And no feature of the story captures it more sharply than the information problem. Classical black holes appear to hide whatever falls in behind the horizon. Later, Hawking's quantum analysis showed that black holes are not perfectly eternal. They can radiate thermally and, in principle, evaporate over immense spans of time. But thermal radiation appears not to preserve all the detailed information about the matter that formed the black hole or fell into it, if taken too simply. That would threaten a principle quantum theory holds deeply. Information is not supposed to be fundamentally destroyed. So, what happens? Is information really lost? Does it remain encoded in subtle correlations within the outgoing radiation? Is it preserved at the horizon in some holographic way? Does the very idea of inside and outside need reformulation? Is spacetime itself, emergent from information, more fundamental than geometry? These are not decorative questions. They are among the sharpest fault lines in modern theoretical physics. And black holes, including ultramassive ones like TON 618, are where those fault lines stop being abstract and become demanded by nature. A black hole does not merely challenge intuition. It cross-examines theory. That is why the singularity and the paradoxes around it should not be narrated as the final spooky chapter after the real science is done. This is the real science at its most honest. The closer we get to the deepest part of the black hole concept, the more the universe reveals that explanation does not always end in closure. Sometimes it ends in sharper demands, better questions, less comfort, greater structural humility. The remarkable thing is that none of this reduces the black hole's reality. It increases it. The object becomes more real, not less, when it begins to strain our frameworks, because that strain is itself part of the evidence that we are not inventing a fantasy for dramatic effect. We are following lawful reasoning to the point where it stops flattering us. The universe is not confusing because the math is weak. It is confusing because the math has been strong enough to carry us into territory where a deeper synthesis is now required. TON 618, then, is not simply a giant dark well surrounded by ancient light. It is a structure that begins in galactic gas dynamics, rises through accretion physics, expands into space-time geometry, and terminates in a question mark built into the foundations of theory. It is one of those rare objects that feels as though it should belong entirely to astronomy, and then refuses to stay there. Follow it far enough, and it drags you into the architecture of reality itself. This is why black holes remain so culturally powerful, even when stripped of cheap sensationalism. Their drama does not depend on screaming danger or spectacular destruction. Their drama is more severe. They are places where physical law becomes at once most successful and most incomplete. Places where reality is both intensely measurable and conceptually unfinished. Places where matter, time, geometry, and information are forced into a confrontation that our current physics can stage but not yet fully resolve. And that changes the emotional weight of the whole story one last time. Because if TON 618 is already large enough to dwarf the emotional scale of our solar system, old enough to expose the violence of the early universe, bright enough to confess the cruelty of accretion, and deep enough to carry us toward the failure point of our best theories, then the black hole is no longer just an astronomical extremity. It is a verdict on proportion. A verdict on the naive hope that the deeper we understand the universe, the more it will begin to feel designed for our minds. The opposite may be closer to the truth. And once that enters the script, the ending is no longer about marveling at a giant object in a distant sky. It is about what TON 618 reveals about the universe that made it, and about the small, local intuition we brought with us when we first tried to imagine it. Because in the end, TON 618 does something more serious than overwhelm us. It reorders what we mean by reasonable. That is the final transformation hidden inside the story. At the beginning, the black hole looked like an outrage of size, a cosmic exaggeration so vast that the only usable human response was awe. Then, awe became pressure. The more honestly we followed the object, the less it behaved like a spectacle, and the more it behaved like evidence. Evidence that the young universe could build extremes earlier than intuition prefers. Evidence that accretion is not just feeding, but violent conversion. Evidence that heavy seeds may have existed, that radiative limits may have been more negotiable under pressure than the gentlest version of the story suggests. That whole galactic environments can become delivery systems for a central appetite. That space-time itself is not a passive backdrop, and the theory remains unfinished where black holes are deepest. By now, the object has changed shape several times. It began as scale, it became history, then mechanism, then logistics, then geometry, then epistemic boundary. That sequence matters because it reveals what TON 618 actually is to the human mind. Not one fact, but a controlled dismantling of familiar categories. Every layer we peel back removes one more place where intuition hoped to rest. Big things take a long time. Darkness is dark. Brightness means easy growth. Boundaries are visible. The deeper theory goes, the more complete it becomes. All of those feel natural. None survive intact. TON 618 is not memorable because it is the answer to a single question. It is memorable because it ruins the comfort of several answers at once. That is what premium science storytelling has to protect in the ending. Not just significance, not just grandeur. The audience must leave with the sense that their first mental model has been outgrown, and that the new one is colder, larger, and more lawful than the old one. Not less beautiful, but less interested in human psychological proportion. We should return, then, to the image that opened the descent. Place TON 618 where the sun is. At first, that comparison behaves like a visual stunt. The event horizon pushes outward beyond the region where our internal map of the solar system still feels complete. The black hole seems impossibly oversized, almost cartoonishly so. But after everything we have now seen, that image is no longer merely a measure of radius. It has become a measure of intellectual displacement. The solar system is not just too small to contain the black hole's horizon. It is too small to contain what the black hole means. Because the real excess was never only spatial, the real excess was historical. A universe still in its rougher youth produced this. A feeding engine this luminous was already operating. Galactic structures were already capable of delivering fuel inward on astonishing scales. Space-time geometry was already ready to curl itself into a region where the future narrows into one direction. And the endpoint of our classical description was already waiting deeper in, where theory itself begins to lose its composure. The black hole is bigger than our solar system. But the deeper truth is that the universe that produced it is bigger than our intuitions about growth, time, structure, and explanation were ever built to handle. That is the real wound the script has been opening. We like to think understanding makes reality more familiar. We imagine knowledge as a gradual taming. The unknown becomes known. The strange becomes clear. The giant becomes quantified. And once quantified, perhaps emotionally contained, there is some truth in that. Science does reduce confusion. It does turn mystery into mechanism. It does replace fog with structure. But sometimes structure is the more destabilizing thing. Because the mechanism, once honestly seen, is less comforting than the myth. A mythic black hole is easy to fear. A lawful black hole is harder to live with. The myth says there is a monster in the dark. The mechanism says the dark is only the beginning. And the real shock is how naturally the universe can assemble monsters under conditions that do not violate its rules at all. That is what gives TON 618 its severe beauty. It is not an exception because nature lost control. It is an exception because nature, under rare but real conditions, remained perfectly within control while producing something our instincts still experience as excessive. The black hole does not expose chaos. It exposes competence at scales we are not emotionally scaled to witness. The universe did not improvise TON 618. It allowed it, and that line should linger, because it changes the moral atmosphere of the entire subject. We often reserve our deepest unease for accidents, ruptures, disasters, breakdowns, things that feel like failures of order. But black holes like this suggest another colder source of unease. Order itself, lawful order. The kind that can, given the right density of gas, the right transport of angular momentum, the right early conditions, the right sequence of mergers and inflows, produce a gravitational structure so immense that our own stellar neighborhood becomes a crude teaching diagram for its boundary. There is something quietly devastating in that. It means reality does not need to become irrational to become overwhelming. It only needs to remain itself for long enough, under enough pressure. And perhaps that is the most honest answer to the black hole's opening promise. The first question sounded simple. How can something be this big? But the mature form of that question is no longer about size. It is about compatibility. How compatible is human intuition with the actual architecture of the universe? TON 618 suggests the answer is not very, at least not without training. We can learn, we can calculate, we can infer masses from broadened lines and time-delayed echoes. We can model accretion disks, radiative feedback, direct collapse, super Eddington phases, galactic inflows, curved spacetime, and the thermodynamic tensions of horizons. We can follow the evidence astonishingly far. But following the evidence is not the same thing as feeling at home inside it. That distinction should remain intact at the ending. Science is not a failure because it does not make the universe psychologically cozy. In some sense, that is its nobility. It tells the truth even when the truth is structurally indifferent to the scale of our instincts. It lets us live inside equations that outgrow our emotional ergonomics. It teaches us to keep going when comprehension becomes less like possession and more like disciplined exposure. TON 618 is one of those exposures. It tells us that gigantic things do not always require ancient gentleness. That light can be the symptom of erasure, that a galaxy can become a delivery mechanism for its own disruption, that a boundary can be real without being tangible, that our deepest theories can succeed brilliantly right up to the point where they no longer suffice, and that the universe, at its most lawful, may still be less intuitive than anything our ancestors would have been willing to call a world. So, when we say this black hole is bigger than our entire solar system, the sentence is true. It is also, by now, inadequate, because the final scale comparison is not between TON 618 and the planets. It is between reality and the mind that first tried to picture it. And on that scale, the black hole may be performing its deepest function, not as an object of fear, not even as an object of wonder, but as an instrument of correction, a way the universe teaches us, with ancient light and impossible gravity, that what feels reasonable is a local habit, not a cosmic law. The solar system remains what it always was, a small, intimate architecture of rock, ice, light, and motion, sufficient for the birth of oceans and memory, and the brief intelligence now trying to understand its place. TON 618 does not diminish that intimacy. It does something harsher and more useful. It puts it in proportion, and that proportion is the after-image this story should leave behind. Not that the universe is simply huge, not that black holes are simply terrifying, not that science keeps discovering bigger numbers, but that the deeper we go, the less reality seems arranged around the scale of human expectation. The universe does not become reasonable at larger scales. It becomes more faithful to laws that were never built for our comfort. And somewhere in the old darkness, more than 10 billion years back, TON 618 is still there, in the only way we can now meet it. Not as a nearby object, not as a spectacle, but as a message arriving late. That nature can build beyond our intuition long before our intuition is ready. And that understanding at its highest level is not the feeling of having contained reality. It is the feeling of having finally seen how much larger reality was than the container we brought to it. And that container matters, because it is tempting, after a realization like that, to turn outward too quickly, to dissolve the whole story into abstraction, into the universe is vast, or reality is stranger than we think, and leave the black hole behind as a symbol. But TON 618 resists being reduced to symbol. Its force comes from remaining stubbornly physical. It is not a metaphor that happens to resemble a black hole. It is a real gravitational structure, fed by real gas, measured through real light, embedded in a real ancient epoch of cosmic violence. The philosophical pressure it exerts is earned only because the mechanism underneath it is so severe, so disciplined, and so indifferent to our need for manageable scale. That is why the object lingers. Not as a fantasy of destruction, as a correction delivered by reality itself. We began with the solar system because the solar system is one of the last scales a human mind can still inhabit emotionally. We know its distances in a bodily way, even if most of us have never written the numbers down. We know what it means for Earth to orbit the Sun. We know the symbolic reach of Jupiter, Saturn, Neptune, Pluto. Even when those distances are vast, they remain narratable. The planets are arranged. The architecture is stable. The map feels finished enough to fit inside thought. TON 618 takes that finished map and makes it provisional. Not because it destroys the solar system in any literal sense. Not because it reaches across intergalactic space to threaten us. It does something colder than that. It reveals that the scales on which our minds first learned order are not central scales in the universe. They are local accommodations, humanly useful, cosmically unprivileged. That realization is not unique to black holes. Of course, cosmology has been teaching versions of it for centuries. Earth is not the center. The Sun is not the center. The Milky Way is not the center. There may be no center in the way older imaginations wanted one. But black holes add a specific brutality to that lesson, because they do not merely enlarge space. They destabilize the categories we use to make space feel narratively safe. Inside their story, brightness means destruction. Boundaries become geometric rather than tactile. Time splits into frame-dependent accounts. Growth becomes a question of whether the early universe was more ruthless than our preferred versions of history allow. The closer you look, the less the universe resembles a grand scenery of things, and the more it resembles a lawful system, willing to produce realities that do not care whether a mammalian brain finds them intuitive. That is the part that continues to echo after the facts are over. Not the number alone, not the radius alone, not even the mass alone. The mismatch. A black hole this large, this early, this luminous, does not just add one more extreme object to the cosmic census. It exposes a recurring pattern. Wherever the universe is under enough pressure, the outcomes stop resembling the pace and proportion human intuition would have chosen. Structures appear too soon. Energies become too severe. Geometry stops behaving like scenery and starts behaving like fate. Theory carries us astonishingly far, then leaves us standing at the edge of a deeper synthesis it has not yet secured. And still the universe remains lawful. That may be the most haunting part of all. It would be easier, in some emotional sense, if TON 618 were the product of breakdown, if it belonged to a category called exception, anomaly, mistake. If we could preserve the rest of reality as fundamentally scaled to reason and place this one black hole in a locked cabinet labeled beyond normal understanding. But that is not what the science gives us. The science suggests something harder. This object is extreme, but its extremity may emerge from a chain of lawful processes pushed into rare alignment, heavy beginnings, violent feeding, gas-rich galactic environments, feedback, suppression, transport, curvature, time. None of it needs magic. It only needs conditions severe enough to let the rules show what else they were always capable of. That is what transforms wonder into something more disciplined and more unsettling. The black hole is not standing outside reality to impress us. It is reality behaving thoroughly. And when reality behaves thoroughly, comfort is often the first casualty. This is why the oldest mistake in science storytelling is to think the highest payoff is amazement. Amazement is easy. Size does much of that work by itself. The deeper payoff is dislocation. The moment the viewer realizes that the real thing being measured is not the black hole, but the distance between human expectation and the actual competence of the universe. TON 618 is a calibration device for that distance. It tells us how quickly matter can become central under ancient conditions, how efficiently gravity can turn infall into light, how galaxies can become funnels, how a horizon can be physically real and experientially silent. How our best classical theory can remain brilliant right up to the threshold where it ceases to be enough. In that sense, TON 618 is not only an object of study, it is a method of education, a harsh one, the kind that does not flatter the student by making the lesson feel natural. It says, what you call obvious is often just local experience pretending to be ontology. What you call reasonable is often a nervous system mistaking familiarity for law. What you call the way things should grow may only be the way growth looks inside a protected corner of one average galaxy orbiting one average star. The black hole does not argue this with philosophy. It argues it with mass, with light, with distance, with timing, with the fact that the early universe, in less than a quarter of its present age, was already capable of building something whose horizon would engulf the intuitive map of our planetary home. That is not a sermon about humility. It is a measurement. And perhaps that is why black holes remain among the few scientific subjects that can still genuinely wound our intuitions without relying on exaggeration. They do not need embellishment. Their mechanisms are already severe enough. Their implications are already sharp enough. The moment you stop narrating them as monsters and start narrating them as lawful structures, they become more destabilizing, not less. The childish fear of being swallowed is replaced by something more adult and harder to dismiss. The recognition that reality may be ordered in ways that exceed our emotional design, and that our greatest intellectual achievements consist partly in learning to remain lucid under that pressure. TON 618 is one such pressure. A giant black hole in a remote quasar, an ancient engine from an unfinished universe, a consequence of gravity, gas, and time arranged without concern for our sense of proportion, a horizon so large the solar system becomes a teaching aid, a center so deep that spacetime itself has to be described differently around it, an interior so conceptually demanding that our current theories begin to reveal their seams. If that seems like too much for one object, that reaction is itself part of the lesson. Reality does not distribute meaning evenly. Sometimes it compresses an outrageous amount of it into a single thing. And that single thing then follows you back into every smaller scale you thought you understood. Back into the image of the sun holding the planets. Back into the ordinary confidence of local gravity. Back into the phrase point of no return. Back into the casual assumption that the universe grows its largest structures slowly enough for intuition to keep up. After TON 618, those assumptions do not survive in the same form. You can still use them locally. You just cannot mistake them for ultimate descriptions anymore. Which is why the final residue of this story should not feel like panic, and not even exactly like awe. It should feel like proportion restored by force. The planets still orbit. The solar system is still what it is. Human life remains small, vivid, intimate, and real. But out beyond all of that, far back in time, far outside the scale where instinct has jurisdiction, there existed, and in some sense still exists in the arriving light, a black hole whose mere existence tells us that the universe can organize enormity early, feed it lawfully, hide it behind radiance, curve reality around it, and then carry our theories right to the place where explanation becomes an unfinished frontier. That is what TON 618 finally leaves behind. Not the feeling that reality is chaotic. The feeling that reality is coherent on terms larger, colder, and less intuitive than the ones we started with. And once you have seen that clearly, the first image comes back changed. Not a black hole replacing the sun, not planets swallowed by darkness. Something more exact. A local map meeting a non-local truth. A small architecture of familiar motion held up for one unbearable moment against a universe that had already moved far beyond it. And that is where the ending stops being about TON 618 alone. Because once a black hole has done all of this to the mind, broken scale, broken timing, broken the easy distinction between light and destruction, broken the assumption that boundaries must feel like surfaces, broken the hope that our deepest theories already form one seamless whole, the final question is no longer, what is this object? The final question is, what kind of universe keeps producing truths like this? That is the matured form of everything we have been chasing. At the beginning, the The black hole looked singular, almost isolated in its excess, like a monument in the distance. But the farther we followed it, the less isolated it became. Its mass pointed backward to ancient seed conditions. Its brightness pointed outward to galactic logistics. Its growth pointed toward an era of violent abundance. Its horizon pointed into the structure of spacetime. Its interior pointed toward unfinished theory. Every serious answer led away from the object and into the character of the universe that made the object possible. TON 618 is not just a black hole. It is a profile of its cosmos. That matters because we often treat extreme objects as though they are decorative outliers, the freaks at the edge of the distribution, impressive but somehow detachable from the main story. In reality, the most extreme objects are often the places where the main story becomes least avoidable. They expose what the rules can do when pushed. They reveal not what is normal in the average sense, but what is permitted in the deepest sense. And what TON 618 seems to reveal is not merely that the universe allows largeness. We already knew that. It reveals that the universe allows a terrifying compression of growth, energy, and causal structure without ever needing to step outside its own laws. That is the true discomfort. A chaotic universe would be frightening in a familiar way. A lawful universe this permissive is harder to process, because lawfulness sounds, at first, like reassurance. Rules imply stability. Equations imply predictability. We are trained to hear governed by law and imagine something mentally habitable. But lawfulness is not the same as emotional friendliness. The equations of gravity do not promise human-scale outcomes. The equations of radiation do not promise moderation. The equations of structure formation do not promise that the early universe will unfold at a pace our intuition finds tasteful. Law is not comfort. Law is only coherence. And coherence can be merciless. That is one of the deepest lessons buried inside black holes. They are not violations of order. They are what order looks like when matter is concentrated beyond the scale of ordinary life. They are the severe edge of the same universe that also makes stars, oceans, cells, memory, and consciousness. The same cosmos that lets a planet remain temperate long enough for language to emerge also, in another epoch and another region, builds quasars bright enough to outshine galaxies and horizons, large enough to make our planetary map look like a local anecdote. Reality is not divided into the reasonable part and the monstrous part. The monstrous part is what the reasonable part becomes under different conditions. That sentence should land heavily, because it returns us to the script's deepest broken illusion. The illusion was never just that black holes are smaller than they are, or rarer than they are, or more violent than they are. The deeper illusion was that the universe is somehow scaled around the forms of order we first encounter close to home. Stable orbits, moderate growth, clear surfaces, intuitive time, tangible causality. Local experience makes those seem primary. TON 618 teaches the opposite. Local experience is a narrow tutorial, not a master key. And once that is understood, the black hole's role in the story changes one final time. It is no longer the destination of the narrative. It becomes the instrument by which the narrative forces a revision in the viewer's sense of reality. It shows that what feels too much may simply be what the universe does when given enough density, enough supply, enough time under pressure, enough early asymmetry, enough space for the rules to finish speaking. We sometimes speak as though science reduces the sublime by explaining it, as though a mechanism, once known, drains mystery away. But TON 618 reveals the reverse movement. The mechanism, if followed honestly, makes the object less mystical and more destabilizing. A mythic giant can be admired from a distance. A lawful giant must be integrated into one's actual picture of the world. The first is entertainment. The second is revision. That revision is the real work of the ending. So, return once more to the beginning, but do not return naively. A black hole larger than our solar system. At first that sounded like excess. Now it sounds like context. The solar system is not the standard by which the universe measures itself. It is the small arrangement through which we learn to think before learning how small an arrangement can be. The planets are still there, still circling, still magnificent in the intimate way that makes life possible. Nothing about TON 618 makes them less real. What it does is remove the unconscious privilege we gave them. It reminds us that our first experience of order was provincial, beautifully provincial, sufficient for us, not central for reality. And that is what gives the black hole its final gravity in the mind. It does not merely enlarge the cosmos, it decenters familiarity. That is a more mature and more lingering form of awe than simple bigness can produce. It is not the awe of spectacle, it is the awe of displacement, the feeling of discovering that your internal scale of what counts as natural was built inside one sheltered corner of a much larger lawful system. TON 618 is not important because it is crazy. That word is too weak, too childish, too anthropocentric. It is important because it is evidence that the universe's own standards for what is buildable, feedable, and structurally coherent are not remotely calibrated to the emotional size of the creatures who eventually study it. We are the ones with the scale problem, not the cosmos. And perhaps that is the final adult version of the black hole lesson. The deeper we go into real knowledge, the less the universe seems arranged to confirm our instincts, and the more it seems arranged to outgrow them. Not maliciously, not theatrically, simply by being faithful to laws that run deeper than preference, older than imagination, and far wider than any local architecture we first mistook for a model of the whole. TON 618 is one expression of that faithfulness. A region where gravity was given enough matter to stop resembling a force and start resembling infrastructure. A region where light became evidence of matter being punished on the way to disappearance. A region where the horizon is not a dramatic surface but a restructuring of possible futures. A region where the classical equations remain brilliant until they become insufficient. A region whose ancient visibility tells us that the early universe was capable of concentrating enormity before our intuition would have granted permission. This is not the story of a cosmic monster sitting far away. It is the story of a universe revealing, through one of its harshest structures, how little our first intuitions were ever entitled to. And once that enters the viewer fully, the emotional residue changes again. The awe cools, the dread clarifies. What remains is not panic, but a kind of severe peace, the peace that comes when something larger than comfort has been seen clearly enough that denial no longer helps. The black hole does not have to come closer. It has already done its work. It has shown that law can be stranger than chaos. That explanation can enlarge reality instead of shrinking it, and that understanding is sometimes the art of remaining lucid while the scale of the real continues to expand beyond the scale of the self. That is not a tragic lesson, but it is not a gentle one. Because the last truth, TON 618, leaves us with is that the universe does not become more human when we understand it better. It becomes more exactly itself, more sharply itself, more visibly indifferent to the habits of thought we developed in one bright, local orbit around one ordinary star. And perhaps that is why the black hole lingers in the mind so stubbornly after the numbers are gone. Not because it is bigger than the solar system, because it is one of those rare objects that makes the solar system feel, for the first time, like what it always was. Not the measure of reality, only the place where we first learned to ask what reality might be. And that is enough to change the meaning of the whole journey. Because once the solar system is no longer the measure of reality, the black hole ceases to be just an object out there. It becomes a mirror held up to the scale of our own assumptions. Not a comforting mirror, a correcting one, the kind that does not flatter the viewer by saying your first instincts were close enough. The kind that says your first instincts were local adaptations, useful for surviving one small environment, and almost nowhere near large enough for the world that produced them. That is the final function of TON 618. Not to terrify us with darkness, not to impress us with size, not even to seduce us with cosmic grandeur. Its deeper function is to make one fact unavoidable. The universe can build with a confidence, speed, and structural severity that human intuition was never designed to anticipate. That is why the black hole lingers after the script ends, because it is not just visually large, it is conceptually invasive, It reaches backward into the early universe, sideways into the life of galaxies, downward into the geometry of space-time, inward toward the limits of theory, and then finally outward again into the viewer's own idea of what counts as a natural world. Very few scientific objects survive that many transformations and remain real at every stage. TON 618 does. It survives the comparison. It survives the mechanism. It survives the mathematics. It survives the uncertainty. It survives the philosophy. And after all that, it still stands there as what it always was, a real gravitational structure in an old region of the universe, fed by ancient matter, measured through ancient light, lawful all the way down until our present laws begin to thin. That combination is what gives it its final weight. A fantasy can be large, a myth can be dark, an exaggeration can sound profound. But TON 618 is harder than all of those things, because it does not need embellishment. The truth is already severe enough. A black hole with a horizon larger than the architecture of our planetary home. A quasar bright enough to outshine galaxies. A growth history compressed into a universe still young. A causal boundary that is not a surface, but a change in what futures remain. A theoretical endpoint where our current descriptions stop deserving total confidence. Nothing has been added for effect. If anything, the most difficult part of telling the truth about a black hole like this is that truth arrives colder than exaggeration. Exaggeration gives you theater, truth gives you proportion, and proportion is what stays. Because long after the exact mass estimate fades, long after the terms accretion disk and broad line region and Eddington limit blur, long after the details of direct collapse and photon trapping and galactic torques settle back into the larger field of astrophysics, one perception remains altered. The universe is not merely bigger than we are. It is less intuitive than we are. That is a far more enduring disturbance. Size alone can be admired. Distance alone can be romanticized. But non-intuitiveness cuts deeper, because it means reality is not just beyond our bodies. It is beyond the first shape of our thought. We have to earn our way toward it. We have to become less provincial in mind than we were by birth. We have to let equations, observations, and disciplined inference carry us into regions where instinct stops being a guide and becomes a thing to be corrected. TON 618 is one such correction. It tells us that growth can outrun emotional proportion, that light can be born from matter on its way to erasure, that a galaxy can become a conveyor belt for its own central wound, that geometry can become destiny, that theory can remain brilliant without being complete, that lawful reality can still feel, from the human side, almost indecent in its scale. And yet there is something strangely clean in that recognition. Because once you stop asking the universe to feel reasonable, it becomes easier to see what science is really for, not to make reality smaller, not to tame it into psychological familiarity, but to make contact with it more honestly, to replace local instinct with earned vision, to let the world be larger than the container we first brought to it, and not retreat when it is. That is the mature awe at the end of this story. Not astonishment at a giant thing, recognition of a giant mismatch. Between local life and cosmic law, between evolved intuition and deep structure, between the sheltered scales that taught us order and the larger scales on which order continues without consulting us. TON 618 closes that gap for a moment by force. It lets us feel, almost physically, what it means for a familiar map to fail, for the solar system to stop being a frame and become a reference object, for a black hole to stop being a monster and become a lawful consequence, for the early universe to stop feeling like a vague prelude and become an active participant in making extremes, for explanation to stop being a path toward comfort and become a path toward harder clarity. That is the residue worth keeping. So, the final image should not be one of destruction. Not planets torn apart, not a spacecraft crossing a horizon, not some theatrical plunge into darkness. The final image is quieter than that, and therefore more difficult to forget. A small, intimate map of home, orbits, planets, distances, the architecture by which a mind first learns scale, held up against an older, harsher fact. And that fact does not sneer. It does not rage. It does not need to. It simply remains more than 10 billion years away in light travel time, born in a universe still young enough to make its existence feel premature, feeding, shining, curving space and time, forcing theory toward its unfinished edges. Still there, not as a threat to us, but as a threat to the quiet assumption that reality ought to fit comfortably inside the forms of thought we learned close to home. That assumption is what the black hole destroys, and what replaces it is better. Colder, perhaps, less flattering, less emotionally convenient, but better. Because now the universe is no longer merely a stage on which strange things happen. It is a lawful system whose depth exceeds our first intuitions at every serious scale, and whose greatest revelations do not make it smaller for the mind, but train the mind to become large enough to remain lucid in its presence. That is what TON 618 finally is. Not just one of the biggest black holes we know, a demonstration that reality was never built to match the size of our instincts, only to be itself. And the moment you really see that, the opening claim changes one last time. This black hole is bigger than our entire solar system. Yes, but that was only ever the first wound. The deeper one is this. The universe that made it is bigger than the version of reality we were born expecting. And understanding does not close that distance. It teaches us how to stand inside it,